we are. Today is Thursday. We're going to be talking about caches this morning. And then this afternoon, Matt Sinclair is going to be talking about gem5's GPGPU model. And then tomorrow, we have lots of little things that we'll be talking about. So there's lots of things that'll take, I don't know, 15 minutes, half an hour to cover. And we'll just kind of bang, 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 hit a bunch of little things. Today, we're not going to be talking about details on how to develop the classic caches, but we'll be diving straight into Ruby and then the on-chip network in Garnet. We're also going to be interrupted in like 15 minutes. Take a momentary break and go get a picture and then come back. Any questions or comments before we dive in? For those of you who want to watch the YouTube video later, we're not going to have a picture of me, unfortunately. The camera power decided to die for some reason. Yeah? What was that? Yes. Yeah. Recorded on the live stream, just without me, just with the screen. So you can't see this pretty face. Okay, so let's dive into this. I'm going to try to get through, and then we can dive into more details about how things work after. Okay, so I'm going to go over a bit of history again, put things in a little bit of context that we said at the beginning of the boot camp, and then also give you a bit of a coherence reminder or introduction for those of you who might be less familiar with cache coherence. Then I'm going to talk about what the components of a SLICC protocol are, how these things fit together. Then we're going to spend most of our time doing an exercise. Unfortunately, I can't ask you to build a coherence protocol because I chose to build one of the simplest ones, this MSI protocol. I was just copying it like straight out of the book, and it took me like a month to get it all working. So I'm not going to do that. But what I've done instead is I took that working protocol and removed some random lines. We have a set of tasks that you will go through to fill in all the missing pieces and kind of see what at least get a glimpse into how I think about debugging kinds of things and after you start building the protocol. Then after that, I'm going to give you a wide-ranging overview of where to find some things, which probably won't make a lot of sense today, but when you come back to this in 6 months, once you start wanting to write a protocol, or in 5 years when you want to write a protocol, hopefully this will help you kind of be able to navigate things. Then I'm going to talk briefly about all the different protocols that gem5 includes, and then a bit more on one particular protocol, the Chai or Kai protocol. I should figure out how to pronounce that. I'm going to go with Chai, because it's written C-H-I, not the Greek letter, so I'm going to go with Chai. Okay, so remember back at the beginning I talked about this gem5 history between M5, which had all this Python stuff that you saw, all the SimObject stuff that we talked about yesterday, as well as a bunch of models of things like CPUs, ISAs, and that really nice modular ISA where any ISA could be used with any CPU model. And then there was GEMS, which had very detailed cache coherence and on-chip network models. So today we're going to be talking about those components that came from GEMS into gem5. So one thing you'll notice if you GEMS isn't exactly the same as the rest of the we've been working over the online, but there's still some things that look kind of weird, and definitely some weird coding styles that you'll see. Okay, so I want to do another brief cache coherence reminder. So let's see, how do we want to do this? So if we have a system with multiple CPU cores, these have some private caches. And then we're going to have a directory. So in here can be really any kind of topology. Let's say all these caches are just connected to the directory, and there's no connections between the caches. And then we have memory. So the reason why we need cache coherence is that if this core does a store to A, it's going to send a message to the directory. This message might be we're going to call it a get m message. Since it's doing a store, it wants to get this cache block in a modified state. The directory is going to look at A and see that it's currently invalid. No caches have A. And then it's going to get A out of memory and then forward or send a response, say data for A, and then we insert A into the cache with some valid data. And we'll be in M state. So then if this core here wants to do a load to A, wants to get the data, we need some way to make sure that this core here gets the updated data that core C wrote. So give me like 5 minutes. So then at the directory, we would have this information that says A is in M state and core 0 has it. So then when this load goes to the cache is now going to send a get S message to get the state. Since it's just a load, we only need shared state. We don't need to be able to modify it. This get S will come to the directory. It will see that A is in modified and core 0 has it. So then we will send a, let's call it an invalidate message from the directory down to this core. This core will invalidate the data, send it back with a put M message. Exactly the details of what these are called isn't too important, but it sends the data back to the directory. The directory writes the data to memory, and then it forwards the data in S state down to this core, which now can have A in S state. Does that kind of make sense at a broad strokes level? Any questions on this? Because we're kind of going to dive off the diving board, high diving board into the deep end here in a couple slides. Why do we send it back to memory? Because that's the way this protocol works. This is what's called a 4-hop protocol. And so if the state of A at the directory is in shared state, it means the memory is up to date with all the caches. That's just the way the protocol is defined. It's not super optimized. Any other questions? Yeah?
Is coherence the same as consistency?
Coherence and consistency are different, subtly different. Coherence guarantees the single writer multiple reader invariant, which basically says that a cache block at any time, there's only a single core that can be writing it, or one or more cores could be reading it. So either you have a single writer, or you have one or more readers. That's all coherence does. System is it's mostly coordinated at the cores with the way the cores interact with the coherence protocol, and defines different. Coherence is all about a single address and keeping that coherent across the system, whereas consistency defines what happens when you have multiple addresses. Speaking of which, there's here, and I also have, if you look in the code spaces which I will show you in a second. There's a full link to the book. There's a 300-page book on consistency and coherence, which I would suggest looking at, get more information about the difference and stuff. Okay, any reminder. Feel free to ask questions. If you're unfamiliar with coherence, I'm happy to answer. This is my favorite thing. I love talking about coherence. Okay, cool. So here's more details about the protocol that we're going to be looking at. So it's an MSI protocol. So we just have 3 states. Cache blocks are either modified, which means a single cache has access to read and write it. It's in shared state, which means multiple caches might have access to do read only, or it's invalid, which no caches have access. So here's all the state diagrams for this cache, and essentially SLICC is implementing. So for instance, if a cache wants to do a load or a store, it's going to need to transition from invalid to shared. So it's going to issue a get S to the directory. And the directory then transitions from I to S. Or if it's already in S, it stays in S. And then it returns the data. Similarly, so I guess I was a little bit wrong before, we send a forward get S if we need to downgrade another cache. A get M is a lot like a get S. And a forward get M also happens as well. Over here, we see what happens on invalidates. And the last one is we always do these puts to write back dirty data. And we also have a write back clean, which is called a put S. So these are moving data from the caches back to the memory. So kind of ignoring the details, any questions on this? Oh, I guess one other thing here, when we do an upgrade request, let's see if I can get rid of that. When we do an upgrade request with a getM, if we need to invalidate a bunch of other caches that currently have it in shared state, we need to wait until we get all the ACKs from those caches, saying those caches have invalidated it. So there's a little bit of extra state where we're counting a number of acknowledgments until we can finally transition to the M state at the directory. Or at the local caches too, I think. Okay, question? Great. Okay, so with that, I'm going to pause for a minute. And I want to introduce Dipak Ghosal. So this is for the live stream.
Oh, okay. Thanks, Jason. So yeah, my name is Deepak Ghosal. I'm the new minted chair of the computer science department. And I wanted to welcome you to UC Davis. I wanted to welcome you to the computer science department for this gem5 bootcamp. And I wanted to tell that many of the things that Jason is presenting are super relevant. I finished my PhD in 1988, and my work was actually on multiprocessing and data flow architecture. And my first paper was in SLICC, and I can bet that if I had a simulator like gem5, my paper would be much, much, much more stronger than it is. And it's just not that. Even now, some of the research that I do in network system research, the network system research is at the intersection of network, very, very high-speed network, and how the end system, which are multiprocessing system with all these cache hierarchies, how they can suck data from the network at a very, very high speed. And for that, also, some of these simulators, like gem5 simulator, would be super useful. And in fact, I have spoken to Jason many times that maybe we should integrate a gem5 with a network simulator. So, I want to thank Jason for championing this and leading this effort. I think this is a super important effort, and I hope that you will take part in this and learn from it a lot and contribute to it, right? Yeah. Really, really important tool. And I can also tell you that I cannot tell you a lot about it, but recently I was in a panel, and many of some of the work that, again, in networks, cloud network research and edge cloud network research, they need this tool. And so whether you're going to do research, whether you're going to go to industry, this will be a super amazing, useful thing to learn and contribute to. Finally, I would say that Davis is a small college town. It's a beautiful college town. I've been here for 25 years, and I hope that you will take a little bit of time to enjoy the surroundings, go to the downtown, and also, if you have a little bit of chance, maybe also go to some of the nearby places. And with that, I would like to essentially thank Jason for leading this amazing effort.
Thanks, Deepak. So I have one more favor to ask you.
Yeah, and one last.
Is we all should be thanking NSF for this. NSF is sponsoring all of you coming here. We are super grateful for that from NSF. There's something else I wanted to say about that. Nope. Can't find it. Thanks, Matt. Cool. Kunal, do you want to see if you can set the camera up? Okay, so we talked briefly about this MSI protocol that we're going to look at the implementation of. By the way, this is figure 8.3 in this book. Oh, let me show you the link to the book real fast. So if you go to, in the bootcamp environment, or in the bootcamp thing, the materials, developing gem5 modules, Ruby, readme.md, and you resync and pull the changes I made this morning, there's a link to this Morgan and Claypool book. Control click. So this is a really, really good reference, or it's also just like fantastic teaching materials on how both consistency and coherence works. They have lots of example protocols, both snooping and directory-based protocols, and this is, I used their simplest directory-based protocol to make this example coherence. Okay. Any questions before I continue on? Yeah.
On like validation, if we pull request are moved from shared to modified, if it receives like one invalid acknowledgement or all the invalid acknowledgements?
You need to count all the NVACs, and you don't move to M until you get all of your ACKs.
All invalid acknowledgements.
Yeah. So the sharers will send NVACs to the requester. The directory tells the requester how many invalidated ACKs to expect, and then the requester counts down.
Like how the request are know that how
Yeah, so the directory is going to keep a full list of all the sharers, so you know exactly how many ACKs to receive. Lots of optimizations there that I don't want to talk about. We can talk offline if you want to know more about how to optimize directory protocols. Any other questions? Yeah.
We have to do a
Please do a git pull on the repository. I'm sorry. We were very close to having everything ready before we started. Okay, so let me remind you again how Ruby works. So we have a bunch of requesters, things like CPUs, things like DMA engines, and there might be other requesters as well, like maybe GPUs or other devices. Then there's Ruby, which is where we're going to implement the logic for all of these controllers. And they communicate between the requesters and Ruby via, oops, sorry. That was a hit page down instead of next. Major mistake. They communicate to Ruby via classic ports that we talked about yesterday. And then similarly, Ruby on the other side of the DRAM controller also communicates to DRAM via these classic ports. So this way, you can really plug anything in that understands how to send and receive memory requests. You can talk to Ruby. And then anything that can receive requests, you can use as a memory controller. OK, so then within Ruby, and I think Marjan showed this picture the other day, but I'll show it again, we have a bunch of controllers. So we have L1 cache controllers, L2 cache controllers, directory controllers. And each one of these controllers implements some kind of state machine to transition between these different states on different actions. And then so we have all these controllers implementing state machines. They also need to communicate with one another. And they communicate with one another through an on-chip network, which is also a black box. This on-chip network could be any topology that you want, and you don't have to worry about when you're implementing your controller, you don't have to worry about the topology. Any questions on that? Okay. So there's a bunch of components to the Ruby protocol. So we have the models for the controllers. So this is like our caches. We're really going to be focusing on the controller state machine, not like the SRAM array where the data is stored. The focus here will be on the state machine of the controller. There's a topology, which is how the caches are connected together, which cache can talk to which other cache, where your routers are, how those routers interact with one another. There's the network model. So that's the model of the routers and the links. And Marjan will talk a little bit about the controller topology and network model after I'm done. And keep in mind here that for Ruby, the goal was flexibility and being able to model a huge variety of different kinds of systems. Never was usability a goal. So you'll find a lot of rough edges, a lot of things that you ask, well, why did they do it this way? And the answer is because they want to be able to model anything, even future things we haven't thought of yet. And so we sacrifice a lot of usability for that. And we talked about the interface being the imports and outports. OK, so we're going to talk about each of these parts in a little bit more detail, and then look at the implementation. So controller models. So these are the state machines of the controllers are implemented in a domain-specific language called SLICC, which is the specification language including cache coherence. Not a very slick acronym. So what's going to happen is, like the ISA language that you saw yesterday, you're going to write code in this weird SLICC language. There's a compiler written in Python for it that then generates the C++ and the Python and everything else that gem5 uses to make the sim objects. So SLICC's original purpose, when this was first thought of in like 98 or 99, was to generate these tables. So if you look through the book, they have a bunch of tables. And the way these tables work are, we have states over here. So for instance, I, S, and M. And then up here, we have events. And so we're describing a state machine. So for instance, if the current state is I, and you get a load, then what you do is send a get s to the directory, and then transition to the transient state ISD. So this transient state ISD means we're transitioning from I, going to S, we're waiting on data. And so this is our, and you'll see this when we get to the protocol implementation. The way these states, the transient states are defined as like, these are the states we're moving between, and then there's an underscore or superscript saying what we're waiting on. Yeah. So you can look at the details of this protocol, and essentially when you're implementing the cache controller, we just need to write this state machine down. And so that's what SLICC is a way to take this table and write it in code form to generate the code. Any questions? Okay. So today, if you run gem5, compile it, and say SLICC HTML equals true, you actually get this output. So you can still use SLICC for this to generate these tables. And this is, you'll notice it is almost exactly the same as this table, except with a lot more details built into it, since this has to be exactly right. Yeah. So this is really useful to look at these HTML files when you're working on protocols. It helps you quickly find errors that you make. And it has a bunch of cool features as well that I won't get into. Okay, so now let's talk about how to create one of these state machine files. Yeah.
So is this table design specific? Like, why do we need to generate it every time? Can we generate it one time?
Yeah, so it is specific to the protocol. So you only have to generate it once for the protocol. Yeah. Does that answer the question?
I mean, I don't understand why we need to have a specification language for like, something that we can generate one time.
Oh, right. We'll see why. So we'll see why, because it generates a lot more than just this table. It also generates all the gem5 code to be able to use it. Okay, so what do these state machine files look like? So they often have a .sm suffix. So you declare a machine, give it a machine type, and then you can put parameters here, which we'll talk about all the parameters you need to have, and then you put a bunch of code in this thing, in this machine description. It looks a lot like C++. I often use C++ for my syntax highlighting. It isn't C++. There's some really weird things that is not C++ that we'll get into. Okay, so once we have the state machine file, we run scans to compile gem5. One of the steps in scans is running SLICC, which compiles this file, and it creates the L1 cache controller.py file. This is our SimObject declaration file that we saw yesterday. You can have, it generates parameters automatically that you can set in your config files, and it makes the cache controller, it's just a SimObject. It also generates L1 cache controller.cc and .hh. These inherit from abstract controller, which is in the Ruby implementation, and it also just implements SimObject exactly like what we saw yesterday. Not surprising at all. Then it also generates a boatload of other files, which are needed to fully implement the controller. All in all, it probably, a state machine file might be 1,500 lines long. It probably generates 10,000 lines of code. There's a lot of code that's auto-generated for you, and this is why we really use SLICC, because a lot of this code is it's very boilerplate, and so SLICC just generates all the boilerplate for us. And also structures it so there's less likely to be bugs in the boilerplate. Okay, so it's important to not modify these files. You don't want to modify the generated files. Caveat, when debugging, sometimes it's useful to modify these files, especially if you're debugging the SLICC compiler itself. It can be useful to modify these files, get the file working, and then going back and modifying the compiler. Which, by the way, I'll say this again later. If you're doing cache coherence research and you're proposing a new kind of cache coherence protocol, which you probably are because it's research, that means you probably need to modify the SLICC language a little bit. I've never written a paper with SLICC and with Ruby that I didn't have to go modify SLICC to get it to work. Okay, so let me give you an outline of the state machine. So there's parameters. Within the parameters, you say you have a cache memory object. This is where the data is actually stored. You have message buffers, which are going to be the buffers that you use for sending and receiving requests. You have state declarations. You declare all the different states that your protocol uses. You have event declarations, which are declaring all the events that can happen. You have a bunch of other structures and functions that are usually copy-pasted. Things like what does the entry look like in the cache? Things like what the TBE looks like, which we'll talk about more in a bit. How to get and set the state, and a bunch of other functions. You then have imports, which are your code that describes what to do when you get an incoming message. So it tells you what event to trigger. You have actions, which are what to do whenever you have transitions in your state machine. And finally, you have transitions. So you have transitions from one state to another, the actions that you want to perform when you're doing that transition, and then how to trigger that transition. Does that make any questions? So again, we're implementing a state machine. So the way this is going to work is we receive a message on a message buffer. So incoming from the network, we get a message to this cache. That's going to go into the import. That import is then going to trigger an event based on that incoming message. So if the message is a forward get S, it will trigger an event to handle that forward get S. So the events that it can trigger are declared in the state machine file. Based on the current state that that cache block is in, we know what transition to go through based on the state and the event. So we use the state and the event to know what transitions. These transitions execute a bunch of actions. As part of these actions, we can access the cache memory, get the data out, for instance, and also as part of these actions, we can send messages into the network to other caches. Questions? I feel like I've just spent 15 minutes describing a state machine to you over and over and over, but that's what this is. Lots of details on how to implement a very complex state machine. Maybe it's a complex set of interconnected state machines, really. One more time, questions? Okay, there will be questions as we start looking at how to do this, I'm sure. Okay, so a bit on cache memory. You can look at the implementation in Ruby structures cache memory. The cache memory stores the data. It stores entries as well as the state for each entry, just like a cache, right? One of the nice things about Ruby is, and SLICC, is that every single protocol can define what an entry looks like. So you can have a 64-byte block entry, or you could even have, in a compressed cache, the entry might be much more complex. It might have, like sectors. You can implement a sector cache. You could also implement entries that cover big regions or things like that. You also have this function called cache probe, which uses the replacement policy to determine what should be replaced. So if you have a request and you need to make an entry in the cache, you can ask the cache, what entry should I be evicting? And then trigger an event based on that. Important, which is something easy to forget, as you're doing this, you need to make sure that you're communicating to the cache memory what's been accessed. So there's a special function called setMRU, or set the most recently used, set the entry as being most recently used. You need to call this correctly. Interestingly, Matt and his student just found a bug in this where all protocols were doing this wrong. So you will be seeing a change coming soon. It didn't affect LRU-based replacement policies. It only affected other kinds of replacement policies, but we were calling setMRU too much. Anyway, just an aside. It's subtle to get these things right. We're adding more tests, so it'll be easier to make sure you get it right. Thank you, Matt, for adding all those tests. Okay, so that's the cache memory. That's one of the first parameters you have. Another parameter is message buffers. So again, these are the way you communicate with the network and send messages to other state machines in the system. So declaring these are a little bit confusing. You have to specify whether they're a to or from message buffer. Often, so you have a message buffer which is a to on one side, and then of course on the other side it's a from. It gets quite subtle getting these things right. So again, we're doing things at a very detailed level, so you also have to include like virtual networks to make sure you don't have deadlocks in your system. And there's this VNet type, which honestly I don't know what it does. But the virtual network numbers are very important to make sure you separate different kinds of requests on different virtual networks. And there's an order to the virtual network accesses to make sure you don't end up with cyclic dependencies within requests. I can go on for days about how to design protocols around this. Know that there's ways to model all this. And then the message buffers have a bunch of functions that you can use, like peek, pop, is ready, to look at the top of the queue. Then there's a couple of special functions, so say you have a request on the top of your message buffer that the cache can't handle right now. Maybe the entry is currently in a transient state, and you need to stall that incoming request until sometime later, until you get to your stable state, and then you can deal with the incoming request. So there's 3 different ways to deal with that stall. One thing you can do is just stall and leave it on that message buffer, but then everything behind that request will also be stalled. So you get really bad head-of-line blocking. If there's other things on that message buffer to other addresses, you're just screwed and you can't deal with them. Alternatively, you can use recycle, which is a thing we can do in simulation, which is not particularly realistic to hardware. You can take that entry that's at the head and just put it at the tail. And then try to deal with things in between and wait till it gets to the head again. If it's still blocked, you put it at the tail again. This is often done when you don't really want to have to fight with getting everything right, and you just want to get it to work. You can use recycle. Again, not particularly realistic. You would probably not do this in a real implementation. Then there's stall and wait, which is a more realistic. So stall and wait, you can take that entry at the top of the buffer, put it in another buffer, and then at some time in the future, wake it up and put it back on the incoming message buffer. So this is more realistic about how caches actually implement things, but then you have to get it right with when you need to wake everything up in that stall buffer, which can be quite subtle, especially for replacements. I say it's been quite subtle. I probably spent weeks of my PhD debugging things because of stall and wait, if not months. Only weeks? Yeah, exactly, only weeks. Okay, so let me pause here, and I'm going to jump over and we're going to start looking at some real stuff. Okay, so I'm going to be going through this readme.md file. We're going to go through step by step how to do this. We're going to do the first few steps together, probably take a break, and then I'm going to kind of turn it over to you to let you just go at it and let us know if you have questions. I think I've given you enough structure that you can figure it out, but if not, I'm happy to help. Okay, so first step is for me to make this bigger. Is to copy the template into the source directory. So gem5 source bootcamp, it already exists. Okay, so I'm just going to copy my all the materials into that. So this is in materials, developing gem5 models, 0.9 Ruby, everything except the README. I guess you could copy the README in there too. Don't copy both the complete and the template. That will confuse things. So you just want to copy the things that are in template. Do not copy the things in the complete directory. Oh, it's scon's ops, not scon's script. Sorry. I did it this morning. Typo. My bad. This should be scon's ops. Okay, so once you've done that, let's go look at that code. Again, this needs to be in gem5 source. Any directory in gem5 source will probably work. Okay, so let's start with the MSI message. I need to fill this in, but before I do that, I need to pull up the answers. So give me 1 second here. Oops, sorry. It's not going to flip for me. Okay. Okay. I think I got everything balanced. Okay, so as I said, you really have to specify everything in a protocol. So let's first start by specifying all the different requests that are going to be moving between different caches. So like I said, you have to do everything from scratch here. So if you look at the, let me jump back here for a minute. So if we look at our table that we're trying to implement, or maybe better, we can look at this. So this is the protocol we're trying to implement. The kinds of requests that we need to make are going to be get s, get m, put m, and put s. As well as we also need to be able to send invalidate requests and also put ack requests. Or is it put ack? Put ack is, yeah, there it is. Put ack is over on the far right-hand corner. So you can look at all those different things that you need to send and then fill this out. So we need get s, and everything needs a description. Come on. So I would suggest writing good descriptions, although I'm not going to do this today. You can look in the completed to see the full descriptions. Any questions on that? Pretty straightforward. You just take your protocol that you've written and then add all the request types that you need. Similarly, you need to fill in the responses. So the response types here are things that if we go back to this, the responses are things that the directory might respond or other owners might respond. So you might have data, and then the other response is an invalidate ACK, are the two responses that we have in this protocol. So you send a request, and then you get that, either data or an invalidate ACK on the response network. So we have data and env ACK. These also need descriptions in the same way. Okay? So you also need to specify all the details of your message. So unlike the packets in the classic caches, which are already structured for you with all the information you might need, you have to create these new messages from scratch. So for instance, a request message needs an address. It needs a coherence request type, the kind of message it is. It needs to say who the request is coming from, where the request is going, the actual data in this data block. You need to specify the message size so then you can track stats on how much data has been sent and received, et cetera. Same thing for the response message. If you have a different kind of message for the response, you need to specify all that. And you might even have more messages than just requests and responses. Like invalidates could be their own message type, if that's what you wanted to do. Questions? Okay. So now that we've defined, yeah. It's a special SLICC file. It's a state machine file in SLICC. I often tell VS Code to treat it as a C++ file, because that will get you 30% of the way there. You still get a lot of squiggly lines, but I think it's more helpful than harmful. Any other questions? Okay, so now let's look at the cache state machine. So as I was talking about before, we have these parameters. These things that you declare first actually show up in the SimObject declaration file as params, just like you were adding yesterday manually. So this means you can set the sequencer cache memory in whether or not to send evictions on the instance of that SimObject in your Python run script. So then we need to declare our message buffers, which I thought was blank, but kind of glad it's not. Maybe the message buffers in the directory are blank. Yes. Okay. See if I have enough room to do this. Okay, so we have message buffers on the right in our cache here. So for instance, we have a request to directory, which is a to network. So if we have a request to directory as a to network, then the directory needs a corresponding message buffer on the other side to receive the responses. So if we have a request to directory in the cache, then we also need a message buffer pointer request from cache on the directory side. This is going to be a from network. We're going to receive requests on this. And then the virtual network is going to be our lowest priority virtual network. So it's 0 on the cache, so we need to use network 0 on the directory as well. And then VNet type is going to be a request network. Ends in a semicolon. So similarly, we can do the other ones, which for the sake of time, I'm going to copy paste. And I would encourage you to do the same thing. If you go to the completed directory, it has all the completed everythings. So we have, beyond just the requests from the cache, we also need a response from the cache, because the directory sends an invalidate, the cache send a put ACK, or an invalidate ACK, or a put. Then we also need, the directory needs to have a message buffer to send a response to the cache, as well as it needs another message buffer. When it receives a request from another cache that it needs to forward, it needs a message buffer for that as well. Okay, so I'm going to paste all those in. Questions on that? So you got to declare all these different buffers that you're going to use. Yeah? So when the virtual network numbers are essentially unbounded. It is an option, or it's a parameter on the network when you create the network in your run script. And so you need to have enough virtual networks in your network in order to handle it. And obviously, not obviously, what this implication is for every new virtual network you add, that's a new set of buffers that you have to have in your routers. So there's trade-offs to having more virtual networks, which is just more SRAM. Okay, so let's see what the next step is. So the next step that I want to do together, and I'm just going to copy paste because I'm feeling lazy, is if we look at the, so we have all these .sm files. So my MSI cache.sm, my MSI directory.sm, my MSI message.sm. And then there was one other file that I gave you as a template, which was empty, which was my MSI.SLICC. So this SLICC file is what the compiler actually looks for to figure out what to compile. And in the SLICC file, you need to specify all the files that are part of your SLICC protocol. This allows you to, although it's rare, have one SM file that's used in multiple different protocols. So you can have a little bit of code reuse. I think that's true of like 2 different protocols in gem5 out of the dozen or so that we have. Not particularly useful, but it's there. So you include those 3 files that I gave you / you created, the message, cache, and directory state machines, as well as another SLICC file which lists all these interfaces that you might need to use. So then once we have this, we ought to be able to compile it, and it should work. Now, before you start compiling, I need to warn you that it's going to be a little bit more complicated. So we're going to build x86 _ my MSI. So we're going to use a different output directory, not x86, and then build gem5.opt. But we need to specify a few extra options here. So one is, since this second parameter in the scons does not correspond to any build ops files in the build ops directory, we need to tell scons which build op file to use as default. So we say minus minus default equals x86, and that's a capital x86. And then we want to override something in that default, which is the protocol. I need more space up here. And use my MSI. So we named our protocol here my MSI, so we can specify that's the protocol that we want to build, and then we can build it. Now, hopefully, I didn't screw anything up. Hopefully you all copy-pasted correctly, and in 5 or 10 minutes, this will be built. While it's doing that, let me jump back over to my README. Cool. And let's take a 10-minute break. Be back a little bit after 10:15, and we can wait for this to compile. And if you have any problems with it compiling, if it's not working for you, let us know, and we can help you out. So see you back here. Let's call it 10:20 to make sure everybody has this fully compiled, because the next step is going to be running something with it. Yeah?
Sorry, what did you get for like the option after like x86
Can you say that a little bit louder? The AC's loud.
Yes, like after you said x86 MSI/gem5 like what was the option again?
That's fine. So I actually did something slightly different since I wanted to use a different output directory. I know it's super hard for you to read in the back. So I said all caps protocol equals the name of the protocol that I added. And then I also added minus minus default equals x86, capital x86. Is that a true statement? Does anybody else need any help to get it to compile? Okay, great. So while this finishes up compiling, for those of you that I helped get it to compile towards the end, I'm sorry. We're going to start moving on, though. So while we're waiting for this to compile, I want to look at the configuration script about the other day. So as much as we've been encouraging you to use the standard library, we're not going to use the standard library right now. So if you look in configs, learning gem5, part 3, and then check out MSI caches. Look at this for a minute. So the MSI caches, this cache system inherits from Ruby system. So like we said, Ruby's this big black box where a request goes in and cache coherence happens. So you need this Ruby system sim object to coordinate all that. You create a network, which again is that cloud between all the controllers. So this network can really be anything that you want. We talked about these virtual networks a moment ago, that you set this as an option on the network. So if you need 3 virtual networks, set it to 3. If you need 10 virtual networks, you're going to be wasting a lot of buffers, but you need 10. Then we create all of our controllers. As Hua mentioned, you need to use list comprehension often to do this, because you can't create a list of some objects and assign it to something that is. Create a bunch of sequencers, and then connect each cache controller, the sequencer parameter, to the sequencer that you created. So this now connects it up. So your CPU is going to be connected to a sequencer, then the sequencer is connected to the cache controller. The sequencers are how from classic ports into Ruby. One of the things that I mentioned about I don't love this coding style is in a lot of cases you have to tell Ruby the number of things, or you have to keep up with numbers yourself to give everything unique IDs. kind of a pain in the ass, but it's just a thing you have to do. Then we connect the controllers up, which we'll see in a second, and then set up all the buffers. So then within the cache, again, you can set these options, like in our SM file, we declared this bool sendEvictions as a parameter. And sendEvictions is something that we can set as the parameter in our run script. And then, as we saw before, that Marjan talked about, we connect all these buffers up as well. Same thing goes for the directory. And then the network, which Marjan will talk about more in a minute, we can set up, specify the way all the caches are connected together. Any questions on that? Other than, clearly I don't expect you to be able to do it, but you at least know where to look for the code to kind of see an example. Okay, so then if we want to run a test, again, this is not using the standard library. This is using all the interfaces that the standard library would use. We import the cache system as MSI caches. Oh, sorry, let me go back. One thing you need to change in this MSI caches file, which it says what to do in the README, is change this check here. So we've recognized that you have to build gem5, a different gem5 binary for each protocol. So we need to check to make sure the gem5 binary that we're using actually has the protocol that we want to use. So since we renamed this protocol to my MSI, we need to change this check here on line 48 in msicaches.py. So then we're going to create 2 CPUs. So we're actually going to run a multi-threaded program. And then we're going to use this threads application, which is a really simple C++ threads application using pthreads. This other stuff doesn't really matter, and then we simulate. Unfortunately, we are still compiling. Okay. Bobby or Mayar, do you think you can help fix this compile error? Yeah. You also have a compile error. Any other compile errors? Has anybody finished compiling? Do I just have a really slow virtual machine today? Oh my gosh. Well, no wonder it's taking so long. Next time, tell me earlier. Thank you. Well, I have a really slow virtual machine if it only has 1 core. Sorry about that, everybody. Let's see if we can prefetch anything here. Oh, let's talk about for a minute, while we're waiting for that. Let's look at a couple of other things in this MSI cache.sm file. So I said we have all these state declarations. So these state declarations are our states like I, S, and M, as well as all these transient states that you have to keep track of. Actually, let's take a pause for a second. Can anyone explain why we need, so our MSI protocol has 3 stable states, M, S, and I. But then in my state declaration, I have like a dozen states. Why do I need all these extra transient states in my protocol? Yeah, go ahead. Say that again? It is like a split transaction. So what is it about the split transaction that requires me to have transient states? Yeah. So moving from I to S is not an atomic transaction. You have to send a message and wait for something to happen. And you need other things to be happening at the same time. So you need to transition into another state, wait for those other things to happen, and then you can transition into your stable state again. So that's kind of the difference between a TBE and an MSHR, as MSHRs are really only for misses that are outstanding, whereas TBEs are for anything that's in a transient state. So you might have a transient state without a miss. So we also have all the events. So for instance, this is an L1 cache, so you're going to have a load coming in from the core, a store coming from the core, a replacement as an event, et cetera. And then, as I said, we have these structures. So your entry, you get to decide exactly what your entry looks like. This is the entry in the cache. What's stored in the transient buffer entry, the TBE, is also up to you. The way the TBE table looks, even, is up to you. And you're going to have multiple TBE tables if you have different kinds of transient states. And then there's, a little bit annoyingly, you have to specify what functions you might use later. So these are kind of like forward declarations in C++. And then there's a few required functions that you have to implement to make sure that other things outside of this controller can talk to it. Things like get the cache entry, set state, get access permission, set access permission, and then functional read and functional write. So then there's the actual ports where we can declare it in SLICC so we can send and receive messages. Out ports need to be declared so you can send a message out. So you give it a new name, the kind of message, and then the message buffer to send on. And then I want to talk about imports for a little bit. Okay, so imports are one of the major secret sauces to getting your protocol to work correctly. So this, for instance, is the mandatory queue, which is the queue where things are coming from the processor. This is the sequencer puts things in the mandatory queue. So in the import, so this looks like, kind of looks like a function call, but then we have that curly brace there at the end. And what this is actually doing is saying this block of code we want to execute on the import, in the import place. And this thing, oopsie, sorry. This is going to magically set up a bunch of local variables for us in our code block. So for instance, it's going to magically set, well, it's going to give us access to some magic things. So the same thing happens when we peek on a message buffer or a request or a import. So if we peek on this mandatory in, again, we use the curly brace at the end, and now we have this magic in message local variable that we can reference. And so we can use the in message. The message type is a Ruby request, so we know it has a line address. And then we can use this to generate our logic that we need. So in this case, we say we're going to get the cache entry for this particular line address. And if the cache entry is invalid, so that means if it's a miss, and if there's no cache available, if there's no room available in the cache for this particular line address, so all the ways in the set are full, then we need to probe the address to find a victim. We get a victim address, and then we trigger a replacement using that victim address. So then we can look at our transitions to see what happens on a replacement. If we do have room, or if it's a hit, then if it is a load, then we trigger a load event. If it's a store, we trigger a store event. And these trigger calls will cause the transitions to be triggered and all the actions within that transition to execute. So this takes 4 parameters: the event to trigger, the address, which will be automatically passed to all of our actions, the cache entry, also automatically passed to the actions, and the TBE, automatically passed to the actions. So you need to do this for all of your imports, all the N-type message buffers, so for instance, forward, as well as responses. Any questions? One thing that's important, the order that these imports come in matters. Your higher priority imports need to be at the top. So for instance, you should prioritize responses over prioritizing new requests. Otherwise, you could get yourself into a deadlock. Or a live lock. I'm not sure which one that would cause. Sure. Give me 2 minutes and I'll be back. Yeah. Okay, so let me jump ahead to let's look at what the transitions look like. So I'm going to have you fill in a few transitions. So a transition is a statement that has a beginning state. So this is saying if you're in state I and you get a load event, then I want to transition to is_d and execute all of these actions. So I'm in invalid state, I got a load, so I need to allocate a cache block, allocate a TBE because I'm going to transition into a transient state. I want to send a getS to the directory, and then I also want to pop this request off the mandatory queue because I'm done with the request and I can do another one. So if we go back, here, actually I'll go here. So you see, if I can find my mouse, in this block, can I zoom in? No, I can't. So if we're in I and we get a load, we need to send a getS to the directory. And then there's a few other things we need to do as well, which are not specified in the book, but needed for correctness. Questions on transition? So if we look at a slightly more complex one, so in this case, if we're in IS, so if we're going from invalid to shared, waiting for the data, and we get a load or a store or a replacement or an invalidate to that line, we want to stall. We just can't handle it. And so you can use curly braces to group things together. And then I don't have a state to transition to because I just stay in the same state in this case. You can also group multiple beginning states together. And you can even do multiple beginning states, multiple different events, and then transitioning to the same stable state. So you don't have to specify the full cross product every time. Okay? So then there's actions. So for instance, so here's an action to send the invalidate act to the requester. So in this action, we can do something. You want to do one thing in your action, usually. So the event that caused this transition happened on the forward network, so we can peek that forward in and get the in message. And then we're going to enqueue a response out. And this enqueue, which looks a lot like peek, has this curly brace here. And so out message is like automatically there in our local, in our locals. And then there's a bunch of other automatic local variables that are populated, like address, which came from the transition or trigger. When we called trigger, we passed in an address. That's what this address is. We can fill out this out message, and then it will be enqueued on the message buffer whenever the transition happens. This last parameter here is a latency to enqueue it. So this is how you add latency to your things in Ruby, is you add latency on the enqueue path to different message buffers. Okay, so really quickly, I went through transitions, how you get in ports from message buffers, as well as actions. Any questions on that? Okay, cool. I'm almost done finally. So I'm going to go back to my README. I did the compile. I did this modification. Number 5. So number 6, I'm going to run my test. It tells me it's going to result in a failure. But let's see what happens. By the way, let me give you a pro tip, which I'm not following. There is a way, I cannot tell you off the top of my head how to do it, to change the linker that you use to a linker that actually links in parallel. And then the linking step goes way faster. I don't know how to do it. It exists. I've seen it happen. Think using like the gold linker might link in parallel, and it might go a lot faster instead of using LDD. Oh, by the way, I guess while we're on compiler stuff, in theory, you can compile gem5 with a huge range of different compilers. I think we have over a dozen different compilers in our compiler tests. Yeah, it.
Apart from if it's very, very old or literally always in the latest releases and even publicly available, you'll be fine.
Fatal. This assumes MSI. I didn't save something. Is it in simple Ruby that I?
Didn't you build it under x86?
Ha, there we go. Thank you. Cool. Okay, so I get an error. Let's look at what the error is. So it says panic, invalid transition. At time 73, there's this address. I got an event data dir no ax in the state ISD. So let's investigate why we got that error. If we go to, so this was the cache controller. So if we go to my MSI cache, search for is underscore d. So here we have a transition, ISD on data dir no ax, and it's commented out. So because it's commented out, we got this event, data dir no ax. We were in state ISD, but there was no transition. So the state machine didn't know what to do. So comment this, uncomment this. And you can fill it in. I believe that the README, oh, So before we do that, let's try to get a little bit more information as to what was going on in the protocol. So if we rerun this, we're going to add a debug flag. Protocol trace. Now if we run with the protocol trace debug flag, scroll back up, we get this really great output, which shows us step by step what the protocol is doing. So this says, at time 0, the sequencer begins an instruction fetch at address 0x9100, or 9100. Then at time 1000, so I guess this was one cycle later with a 1 gigahertz clock. At time 1000, the L1 cache begins a load, and it transitions from I to ISD, again on this same cache line. Then 6 cycles later, so I guess it takes 6 cycles to go to the directory, the directory got a getS event and transitioned from I to S underscore M, again with the same line. And then it took, looks like, 64 cycles, or 64 nanoseconds. Later, the directory got a memory data. On memory data, it transitioned from S underscore M to S, and same line. So then, sometime later, we don't have the exact time, the next thing that happened was the cache got a response, which is what triggered the data dir no ax event, and then we panicked because there was no transition for it. So now I'm going to turn it over to you to try to figure out how to fix this issue. After you fix this one, another one will happen. See if you can fix that. After you fix that, another one will happen. See if you can fix that. Let's do this for like 15 minutes, and then I'll fix some of these things. We'll come back in 15 minutes and then resync. And I'll be walking around to help out as we do that. Every time you change something in the protocol, by the way, you need to recompile to get it to work. Any questions or anything before we break out into this task on our own? OK, great. To remind me to put on a mic. Okay, and then the next step was fill in the right data to cache. Okay. So this is a little bit weird. So when we write the data to cache, what we're going to do is peek at the response endport, because the data is on the response endport. We're going to peek at it. We want to make sure that this cache entry variable, which is just automatically there in an action, we need to make sure that this is valid. Because if we didn't have a valid entry, we couldn't write anything to it. This statement would cause a seg fault. And then we're going to set the data block to whatever the data is in the end message. Again, the end message is a magic local variable that got populated by this peek. Okay. So then the next step is, why do I have an assert failure? So if you got to this point and you ran it, this assert would actually fail. So it would fail because the cache entry is not valid. You never set the cache entry. So that's because we had not allocated a cache block yet. So if we fill this allocate cache block in, so here we have the opposite assert. Whoop. Here we have the opposite assert, where we're asserting that the cache entry is invalid. So remember again, this cache entry is just automatically there, and it comes from the trigger statement. We need to assert that there is cache available. Like, we better have probed and replaced something to make sure that we can allocate a new cache entry. Then we actually allocate a new cache entry by calling cache memory allocate. We use the type entry for this. This is the address. And then we call set cache entry. This is a magic function that then means all other future actions that use this variable cache entry will have the pointer returned by this allocate function. So there's lots of magic functions. I'm not going to try to explain them all to you. They're documented pretty well in the part 3 of learning gem5. Yeah, lots of magic functions that just kind of exist. Okay, let's see. So then when we ran it, it says possible deadlock aborting. Let's do that real fast. This time. We saw one type of error, or two errors so far. One was an invalid transition error, which is my favorite kind of error to see, because I know how to fix it. I add the transition, figure out what to do in the transition. My second favorite error is an assert error, because I put an assert somewhere, and I can find where that assert is and figure out if that assert is invalid or if I did something wrong. I can trace back the assert. My least favorite kind of error, my second least favorite kind of error, is deadlock detected. That means something can go right. Tracking those down can be quite difficult, especially if it's a live lock situation where other things are also going on. You're not going to run into this example, but my least favorite kind of error is the error where the data is wrong. It's like, oh, that's incoherent. There's just a protocol bug somewhere. Now I have to go back in time hundreds or thousands or millions of nanoseconds and trace this address and see what happened. I've generated protocol traces in the tens of gigabytes that then you had to trace back through and try to figure out where something went wrong. Tens of gigabytes is nothing, Matt? 200 gigabytes. But 10 gigabytes are one from grabbing and ignoring everything else. There's actually a clever thing you can do. So when you're running with debug flags, there's an option you can do which is --debug out to specify file to write into instead of the standard out. That can be useful. Then what you can do if you really need pipe as the output file, then what's happening is Linux is writing to that named pipe in memory and then grep that named pipe, and then in memory it will be doing all the grepping instead of doing it through a file. So that can be quite a lot faster than writing to a file and then grepping a file, especially if we're talking about things that are in bytes. Okay, so that worked. So now let's run this again and look at the error. Oh, there's another invalid transition error. Data dir no ax state s. Oops. That's a little annoying. I didn't say that you needed to do that. There it is. No? Oh, I changed the wrong place. Darn. That's really frustrating. Isn't this something that my R just told me that was a common error that people need to look out for? But I just did the same thing, though. I modified the file in the wrong directory. Okay, this is better. Sorry about that, everyone. So clearly we're not going to get through all this. I'm going to stop here in about 10 minutes. Let me fill this in while I'm waiting for it to go. So one of the things I'm filling in here is sending a getM message. Okay, I want to briefly talk about So when you enqueue, we talked briefly, this is the latency we're enqueuing. Your out message, to the out message is a destination is a bitmap of all the destinations you want to send this to. So it's like a multicast message. You can send a broadcast and set all bits to true and send it to everyone, or you can set a single bit to true to send it to one machine. So that's why you say destination.add, and then you often use this function map address to machine. If you have a multi-banked LLC, or if your directories are corresponding to different memory controllers, which are interleaved in some way, you can use this function map address to machine to get a particular. These destinations are filled of machine IDs, which contain a type and a number. So if you have like 2 directories, you'd have machine type directory, machine number 0 or 1. And then you often need to keep the requester. Under the request, it knows who to respond to. Destination to the requester for a response. Okay, so hopefully this time when I run this, damn it. Hopefully now I get a deadlock detected. Beautiful. Okay, so we see quite a few more things happened here than last time. So the L1 cache got the data to no ax, and then it got a load hit. So the last line there at time 75 nanoseconds says the L1 cache got a load. It was in state S. We stayed in state S. It should be a hit. But what happened was I didn't have anything to do on the hit. And so it never returned the result. And so it says possible deadlock detected, issue time 7400, and the current time is something high. So essentially there's this counter that says what's the last time that any transitions have happened. If nothing happens for a particular address for, what is that, 100 billion cycles or something, then it says there might be a deadlock. Or it could also be a live lock as well too. So that means we need to fill that in. Questions? So you can continue debugging. I want to mention one thing. If you go through all of this README, eventually you're going to get to a place where when you run this, it actually runs to completion. Or, yeah. So I think at some point it actually runs to completion. And that even though there's still fill this in. So that's because the program we're doing is like a user level program that has threads communicating, and it doesn't actually exercise all the possible transitions. So to get around that, we have something called the Ruby random tester. So the Ruby random tester takes a slightly different config file, and the way your cache is set up is slightly different. But to run it, I have an example here called rubytest.py. And what it does is it looks at all your caches, or all the things, all the requesters in your system. It instantiates a number of cores. And then it sends requests out of these cores such that you're most likely to get interference between different caches. So 2 cores both issued for the same address at the same time. So you try to get more of these corner cases in your protocol. So if we run that, often the errors will come up faster than what happens when you run real applications. Or to trace back. So for instance, I just ran the Ruby random tester with this, and even on the very first access, it got an error. Whereas my other one was going through a few different instruction fetches. So that's really, the Ruby random tester is a very, very useful thing to do when you're debugging. Now, my last thing that I was going to talk about was some of the statistics output, which I don't think that I can. Oh, maybe I can. So let's try. No, I can't. I'll tell you what we're going to do. I'm going to rebuild this with the protocol that actually works. While that's rebuilding, I'm going to turn it over to Marjan to talk about the networking side of the system, and then we'll come back and look at some statistics that Ruby gives us that there's no way to get out of the classic caches. See, before Marjan starts, let me double check that I went through most of this stuff in my. Cool. Okay. Awesome. I think I got through almost all that stuff. So let me turn it over to Marjan.